As you know, my name's Clinton Hilliard. I'm the programs director and for the chapter. Just like to welcome everyone again. A couple preliminaries. As you guys know, we regularly raffle off a prize at the end of these things. So we're going to do that tonight to all attendees, or whenever all attendees are eligible for that. That prize is going to be a book written by our presenter. It's called Holistic Thinking. So hold your questions till after the talk. Feel free to put questions in the chat, though, if you're thinking of them right then and there. And then Dr. Kasser will answer them all at the end. So this evening, we're very honored to host one of Incose's fellows, Dr. Joseph Kasser. He's practiced systems engineering for over 50 years. He's also been an experienced project manager for more than 35 years and an academic for more than 20 years. Dr. Kasser is a very prolific publisher and likely authored more papers for Incose International Symposia and regional conferences than probably anyone. In 2004, Dr. Kasser was an invited U.S. Air Force Office of Scientific Research Window on Science Program Distinguished Research Visitor. He has been a recipient of the National Aeronautics and Space Administration, NASA's Silver Snoopy Award. If you're not familiar with that is, that's a manned spaceflight awareness award given for quality and technical excellence in performing and directing systems engineering by NASA. He's was introduced as an Incose fellow, but he's also served on the Incose member board as an Incose ambassador. He founded Incose Australia as the Australian chapter for Incose, and he served as the chapter's very first president. Dr. Kasser now continues to extend his career as systems engineering mentor and coach. So without further ado, I'm going to now hand this over to Dr. Kasser, and he's going to attempt to try to play his talk as a video, and then we'll, like I said, we'll follow up with the question and answers after the video is played. So Dr. Kasser, can you unmute yourself? There you go. There you go. All right.
Thank you for taking the time to attend this presentation. The logo up in the corner there is from the last time I made a presentation to the Incose Chesapeake chapter. I'll start with some apologies and a warning. This talk perceives traditional systems engineering in a different way. It's based on a different paradigm. It's not the Incose paradigm, but it's worked for me 100% of the time on simple and complex projects. The perceptions may challenge you. The perceptions may offend you. If they challenge you, good. If they offend you, I apologize. But the talk is designed to make you think. It's to take you out of your comfort zone. Some of the information may be dated because I've been doing this research for 20 years or so, and I've just pulled in slides from earlier presentations. It's all about systems thinking, so let's take a look at problem solving from the systems thinker's perspective. Systems thinkers say when you have a problem, conventional thinking isolates the parts to understand the behavior, but that's not what you should do. What you should do is explore the emergent nature of the system as a whole and understand how it works together with its adjacent systems so you can deal with the problem at that level. Okay, fine. It's a cold morning in the winter. The car doesn't start. How does understanding the emergent nature of the car as a whole and its interactions with the other cars and the traffic light and how you use the car help you with the problem of dealing with the car not starting? You have to use conventional thinking. You have to understand that the cause might be a dead battery. because you've got that from conventional thinking. And then conventional thinking and systems thinking doesn't really help you understand where the solution comes from. People tell you to think out of the box for the solution, but they don't actually tell you how to do it. To cut a long story short, years and years and years and years of research took place. I had to move from Australia to England and then to Singapore to finalize the research. And I came up with something I call the holistic thinking perspectives based on two things. The first thing was all the perceptions of systems engineering and systems thinking I was seeing, or partial perceptions of a whole, in a similar way to the parable of the blind men feeling the elephant. They all felt a different part of the elephant, and they all thought they came up with a different animal. Let's say systems thinking, and then later on systems engineering, is the elephant. And what I did was I looked at the different perceptions in the literature and actually created the elephant, the one that nobody talks about. Or actually it's the two that nobody talk about, because there are as many different versions of systems thinking as there are of systems engineering. So at Cranfield University, leveraging on the work of Barry Richmond's 7 Streams of System Thinking, we came up with a number of systems thinking perspectives that were presented at Incose in Holland in 2008 and were later renamed the Holistic Thinking Perspectives. And there were 9 of them. So there's the big picture perspective and the operational perspective, which broadly translates into systems thinking. There's the functional and structural perspective that translate into conventional thinking. And then we went beyond that. We looked outwards into generic, continuum, and temporal. Generic is the similarity between this system and other systems. The concept is used in software where objects inherit. So your system can inherit characteristics from the generic type of system. The continuum perspective deals with differences between this system and other systems, or differences between the parts of the system. The temporal perspective deals with behavior over time. And then there are 2 other perspectives. The quantitative perspective, that's where all the numbers come from. And right away I can look at this and say, a requirement consists of functions and numbers. So a requirement needs to be looked at from 2 different perspectives. The scientific perspective, which is the outcome of the thinking process. So the first 8 perspectives are what our systems engineer Sherlock here observes, and after doing a little bit of critical thinking, out comes the scientific perspective, which are his inferences. And I group them this way. External is systems thinking, internal is analysis, progressive, and remaining. And I'm going to explain these in a moment, and then I'm going to use them to look at or perceive that elephant called systems engineering. But first, which perspective is needed? Now remember, the car wouldn't start. So if the car wouldn't start, I actually need an internal perspective. But if I want to use the car to do something, to go somewhere, then I need the external perspectives. The internal and external perspectives are useful for understanding the situation. Now, not every perspective is applicable in every instance, but where do the solutions come from? They come from the progressive and remaining perspectives. And I'm going to show you that when I comment on systems engineering and then show you some of my conclusions. Consider a camera. From the big picture perspective, we look at where cameras are used and for what purpose. Operational, that's what we're doing. Capturing images, transporting it, viewing images, adjusting it, charging the battery. Functional are capturing images, the actual details of how the image is captured, storing them, retrieving them, deleting them, how the battery charging functions work. It's the how part of it. Structural perspective, we're looking at the body of the camera, the case of the camera, and the physical aspects of the charger. Generic perspective, other ways of capturing images, such as painting, sketching, and so on. Continuum perspective might deal with different types and models of camera and different materials used to construct the camera. And the temporal perspective would be the evolution of the image capturing media. It started off commercially with photographic plates, then it went to film, different sizes of film. We're now into solid state memory, and somewhere and sometime in the future there will be a new technology for storing images. The quantitative perspective deals with number of pixels per inch, the characteristics of the lens, the price of the camera, and the memory sticks and so on. And the scientific perspective will depend on the problem or the issue as we perceive the camera from different perspectives. And I'll show that here. When I think about a camera and I want to understand how a camera works, I use the functional and structural perspectives. That's conventional thinking. And I think about the system as the camera, and it's a closed system. On the other hand, when I want to think about capturing images, that's an operational perspective. Then I think about the camera and the operator and whatever I'm taking a picture of, and that's also a closed system because I abstract out everything else. If I'm transporting the camera, then I'm thinking about the camera, the operator, and the camera case. Again, everything else is abstracted out. If I'm recharging the camera, then my system contains the camera, the operator, and the charger as a closed system. Not your conventional way of thinking in most cases. Going for unconventional ways of thinking, let's take a look at systems engineering from different perspectives. From the big picture perspective, we see all sorts of things, and I'm not going to go into every single one of them because I've only got 45 minutes. So there are things like the principle of hierarchy, systems engineering education, which is something I've been very concerned with over the last few years. Systems thinking, sort of context for systems in different domains. There are different views and opinions on systems engineering. It's performed in projects, and there are processes, products, and problems. Systems engineering overlaps with other disciplines. There's a major focus on process in Incose and DoD, and now there's this new fad called model-based systems engineering. Some of you will have seen this. This was presented to General McChrystal in a briefing in 2011 or so, and his comment was, when we understand that slide, we'll have won the war. This slide totally ignores one of the basic principles of systems thinking and beyond, or systems engineering actually. It's the way we have managed complexity like this over the centuries. And let me give you an example. Abstract out the information and just look at what's there. You'd see something like this. So where is the system or subsystems? Well, I've colored them in parts corresponding more or less to the colors in the original chart. How do we deal with this? Well, we break it up. We call it 6 systems. And we hide everything that's inside each of those systems, so this conforms to Miller's rule. 7 plus or minus objects that the human brain can only think about at any one time. If I want to look at the behavior of part of it, I abstract out the parts that I'm not interested in. If I want to look at what's going on inside the system, I abstract out everything except what's going on inside the system, or inside this system, or inside this system, or inside this system, and I realize, whoa, that was a poor choice of partitioning because those 2 lower objects are not coupled to the 3 higher objects, or this one. The square is not coupled in any way to the other 2 objects. Man, I need to change my system partitioning, or this one. So by just looking at it this way, I've reduced the complexity of the system, and I've also seen that I need to change my architecture. Do you realize it's all fractal? If I take a look at this thing here, and I put a boundary around it, and I fill that boundary in, and then I zoom out like this, it's surrounded by other systems going on. And so the principle of hierarchy says you deal with the level that you need, up one and down one. It's not my principle. It's been stated many times over the years. And that leads to the system optimization paradox. We're taught in class that you don't optimize a subsystem independently, you optimize the system as a whole. Oh, great. Because every system is a subsystem of some larger system. So how do you optimize the system? I'll leave that question with you. I know how I do it. If I go back to looking at systems engineering education back in 1999 to 2006, and I'm not sure it's changed very much either from what I see, we focus on what's easy to teach. We teach parts. Different universities teach different parts. I found that out 10 years later, as I'll explain in a moment. We show relationships. We don't go into details. We do a lot of teaching of the what, but not the how. And we don't teach the basic building blocks of solutions. And yes, there are gaps there and we ignore them. I keep finding myself telling students, and you won't find that in the book, because I was teaching something that was in one of those gaps. And when I was living in Singapore, I had a contract with CRC Press to write a book on systems engineering based on what I was teaching. Okay, fine. I ended up saying I couldn't do it, because when I started writing the book and filling in those gaps, it filled 4 books. So I ended up writing 4 books. We teach things that are not representative of reality. We ignore the paradigm of change. We talk about get all the requirements up front. But wait a minute, the requirements are going to evolve. We don't teach how to manage that. We also don't use the optimal pedagogy or technology. That's changing now. Most of the courses I've seen were all lecture-based, well into the time of problem-based learning and learning by activities. And we mostly teach process or doing it by numbers. And systems thinking isn't taught very well. There was a talk at the Chesapeake chapter last month about the benefits of systems thinking. Well, I was able to do that 20 years ago. I could teach the need for systems thinking, the history, and then I had to tell people, when you're doing it, you'll know it. I didn't think that was very satisfactory, so I ended up moving to the UK to work out how to do it. We know about system dynamics, we know about Checkland's soft systems methodology, and then causal loops, which were publicized in the 5th discipline by Peter Senge. Linear thinking is bad, is it? And then there are vendors and traders out there that will tell you, my approach will solve all your problems. When I was in the UK, I attended an Incose UK symposium, and somebody was telling us in the keynote, I think it was a keynote presentation, but I'm not sure, on Checkland's SSM and how it would solve all systems engineering problems. That's Maslow's hammer syndrome. We don't teach when, where, and how to apply systems thinking systemically and systematically. That's probably why there's so little of it about. And basic influencing literature is generally coming from operations research, not systems engineering community. When we're teaching systems engineering, when we taught the systems engineering process, we used the egg diagram. And I've seen this in various other places. How many people really understand that? We can go through all the words. This is a what. How do you actually do that? You've got requirements, you've got functional analysis, you've got synthesis. How does this relate to the different states or phases in the system development process? This is the way we taught it in 2006. Would you care to explain that? And what was the result? Let's try a different way. Let's teach it as a problem-solving process based on Derek Hitchens. So we've got milestones when we look at it this way, and this is where we can look at it from a whole top view. It maps very nicely into the waterfall. We can show it over the life cycle like so. And it links very nicely into the whats and hows of systems engineering. A what is the problem input to the state. A how is the solution produced by the state, and that creates the what for the subsequent state. So for example, the problem early states is to create the requirements, for example. Once we have the solution, which is a set of requirements, that becomes the problem to the design state, because now they have to design a system based on those requirements. They output designs, and that becomes the problem to the construction people. And so I would much rather demonstrate the systems engineering process this way than in the egg diagram, because this really shows it's an iterative process, which was Howard Eisner's definition of systems engineering back in 1988. Another look at the system development process from the University of South Australia was we started off with a stakeholder requirements, we had a systems requirements, and something happened, and then the system was in being. What did we say happened? This was some discussions on systems engineering between Jenny Clothier and Stephen Cook back when I was at UniSA. I'm not surprised when I see that. Look at the books in systems engineering, including mine up there. You've got all these books. And they're all different. There's some commonality like requirements and architectures and testing, but otherwise they're all different. So if systems engineers can't agree on what systems engineering is, how could we expect to sell it to organizations to allow us to bring it in there to improve them? And by the way, Howard Eisner's latest book, What Makes the Systems Engineer Successful? I've read the book, and I will state that most courses in systems engineering as taught in universities do not include much of what is in Howard's book. And then we ignore the principle of hierarchies. Take a look at this. How many people are willing to admit they don't understand it or are willing to say it's wrong? It totally ignores Miller rules. There are 3 levels of the hierarchy in the drawing, and then I start looking at the details, and there's no direct connection between systems engineering knowledge and Incose. It's wishful thinking because it puts Incose in charge of feeding information to graduate programs in systems engineering, and academia is not going to go for that. The body of knowledge does not inform the textbooks, and the body of knowledge does not inform academia. I'm not sure what this drawing is actually supposed to represent. Take a look at the structural perspective. It's a static view. It deals with architecture, components, subsystem boundaries, and systems engineering standards. Do you know there are no standards for systems engineering? 499 is develop a systems engineering management plan. By the time they got to 499A, they took out the word systems and it became engineering management. Or 632, it's the process for engineering a system. Or 1220, it's the management of the systems engineering process. And if you look at the standards and you try and take the categories of systems engineering and map them into the standards, you find out that those early stages of figuring out what the problem and the solutions are not in any of the standards. And this is based on a table in Eric Honor and Ricardo Valenti's paper at the CSSR in 2006. And look at DoD directive. It required systems engineering. Acquisition programs shall be managed through the application of a systems engineering approach, so on and so on. And it emphasized the use of systems engineering. But DoD 5000 gutted systems engineering because it removed the front end and called it IPPD. And I'm not sure if it led or reacted to the situation where systems engineering was not doing very much in the front end. Now look at the DODAF. The DODAF was a great idea, but the purpose of the DODAF was communications equipment. But suddenly it's applied everywhere to all sorts of equipment. And look at the amount of information in it. That's ridiculous. Not my opinion. 45,000 man-hours according to Scott Davis in 2003. Well, do we really need that? For those of you familiar with the DODAF, the operational view 1 describes the use of the system. Here's my view of the DODAF in use. Dilbert has created the DODAF that his customer has asked for. The customer says, I don't understand any of it. I can't tell if it's right or if it would embarrass me. I can't ask for a second opinion without looking stupid, and I can't distribute it because it might be wrong. So I'll put it on this pile and hope something changes. Secretary asks, should I shred your pile of indecision, make it look like an accident? What a waste. The temporal perspective looks at how the system behaves over time. It leads to patterns of behavior, leads to prevention, availability, maintenance, logistics, reliability, lessons learned, and so on. So here's a light-hearted look at the degree of micromanagement in systems engineering standards based by the number of pages in the document. And I haven't taken it past 2002. I'm afraid to. There were systems engineering successes. Look at the Apollo program in 1970. That engineer working on that box is me when I was handsome. The box is probably inside the thing on the lunar surface right in the front of the picture. That was the ALSEP that the astronauts set up on the moon. Successes in Singapore, in the social system, the economic system, and the defense system. And Dr. Goh King Sway was the chief systems engineer who put it all together. Systems engineering is poorly practiced, but it need not be. I'm going to brag a little here and say, if you look at that strike fighter overrun, I predicted that at the Incose symposium in 2001. And there's a lesson learned from that if you're going to predict the future, predict it in a conference that is small or a publication that's not widely read. Because then when you're wrong, nobody will remember it. And when you're right, you can always bring it out and brag. But then when you do that, you upset other people. And what were the top 5 systems engineering issues in 2003? Lack of awareness of the importance of value, timing, accounting, and organization structure of systems engineering on programs. Has anything changed? Adequate qualified resources are generally not available within government and industry for allocation on major programs. Not sure much has changed there. Insufficient systems engineering tools and environments to effectively execute systems engineering on programs. Okay. Requirements definition, development, and management is not applied consistently and effectively. Not sure anything's changed there either. Poor initial program formulation. Okay, let's just address number 3. Ever heard it's a poor workman who blames his tools? And how did Incose address these issues? No further comment. Nobody's heard of systems, even very large systems, are not developed by the tools of systems engineering, but only by the engineers using the tools. There's also a saying that a fool with a tool is still a fool, or words to that effect. Or perhaps a fool with a tool is a more effective fool. The focus in the literature is on people, not on process. And yet Incose has been focused on process for years and years and years. I have a theory as to why that is, but I'm not going to present it today. Failures due to poor practice. Inadequate systems engineering in the early design and definition stages. Well, we talked about that. The standards don't cover that area. Or there's a definite link between escalating costs and the ineffective application of systems engineering. My conclusion is standards might help you produce the wrong system more effectively. If you think about that, we've been teaching systems engineering now for at least 20 years. We're teaching the wrong things. We're not teaching the right things. There are all sorts of gaps. So do you wonder about these failures of systems engineering? And I'll come back to that in a moment. In the continuum perspectives, we see dichotomies in complexity, systems and systems of systems, and then we see differences, life cycle models, roles and activities, the A and the B paradigms, domains of the problem, types of problems, complexity, and types of systems engineers. Some of these things you've probably never even thought about. The systems engineering process, the great mantra of systems engineering, some of them, is follow the process and all will be well. Okay, which process? This one? This one, this one, this one, this one. And then we have the A paradigms. The A paradigms is the old paradigm of systems engineering. It starts with the concept of operations. We understand the situation. We define the problem, we define the solution in the form of a system architecture, then we produce the requirements, and then the subsystem design and the rest of the process follows. The modern paradigm starts with requirements, and then we build a model or a concept of operations, or whatever you want to call it, and then create the architecture, and then go through and do the subsystem design and so on. And I can tell you in a different presentation, I've even written it up, and so's Derek Hitchens, as to how this happened. And then there are three different domains of the problems, and you won't find this in any textbook either. Consider the example of traffic congestion. The problem is to reduce the traffic congestion. The solution is a subway system, but the implementation domain, you need to understand tunnel boring and road traffic management, so how you divert traffic while you're creating the stations and so on and so forth. And if you want a really optimal solution, you need to understand all three different domains, and you will not find this in any of the textbooks. And then there are 5 types of systems engineer based on observation, and it's also reinforced in the innovation literature. The type 5 is a problem formulator and problem solver. The type 4 has the ability to examine a situation and define the problem, but cannot conceptualize a solution. Type 3 can conceptualize the solution and plan the implementation. Type 2 can follow a process to implement the physical solution system, and Type 1 has to be told how to do something. Think about putting a Type 3 systems engineer into a situation where they have to understand the situation and figure out what the problem is. They can't do it. One of the reasons for failures of systems engineering, the wrong type of systems engineer in the situation. You've heard about situation management, generic thinking. Well, there's situational systems engineering as well. From the generic perspective, what systems engineering is similar to? Is there another discipline it's similar to? These are the things that are struck out, are things that I'm not going to talk about in this presentation. Systems engineering is similar to math. Math is a set of mathematical tools for remedying mathematical problems. It's used in all disciplines, and it's structured as pure and applied math. So systems engineering as an activity, to me, is a set of problem-solving tools for remedying complex problems. It deals with parts and their interactions as a whole. It's used in all disciplines, and it's structured as pure and applied systems engineering as used in domain systems engineering. And there are 3 types of systems engineering, the activity. Pure systems engineering, that's systems thinking and beyond, the cognitive skills, problem formulation, and so on. Applied systems engineering, that's requirements, architecture, V&V. That's what we do as systems engineers, and then we do it in the domain. And it's similar to mathematics. By organizing systems engineering in this way, I can now figure out what I need to teach. From the operational perspective, we deal with what systems engineers do, scenarios or use cases. That's how I developed what I needed to teach. One of the ways to generate the requirements for the course was, what do systems engineers do? What knowledge do they need? Well, they work in processes, they work in teams, they create products with different degrees of complexity. But one of the things systems engineers don't produce are systems. Engineers produce the systems. Systems engineers might specify them, and they might get involved in the integration and testing, but they don't actually produce systems. Do you think about it that way? The scenarios that we work in are, we use pure systems engineering thinking tools in applied systems engineering, conceptual design, requirements management, architecting, testing, integration, V&V, engineering management, and so on. For those of you who learn through vision, I can show it like this. Systems engineers use cognitive skills while performing activities in 3 domains. The cognitive skills are the pure systems engineering, the activities are the applied systems engineering, and they do it in the domain. And there's the relationship. Now, the scientific perspective. That's the outcome of the thinking process. We have an issue, problematic situation, system, whatever it is. We perceive it from the different perspectives, and then the scientific perspective is the statement of the problem. We need to filter out the pertinent information. It's a hypothesis, formulation and then we go ahead and test it. You can think of the system design process as testing a hypothesis, where the hypothesis is the set of requirements that we think will resolve the customer's problem. Then we go through and build the system and test it. When the system works and the customer's happy because it's the system the customer needs, our hypothesis was confirmed. A design is a similar guess or a hypothesis, and then in science there's research questions. It's basically the outcome of critical thinking. Critical thinking also has a large number of definitions, and I want to give you one of the basic examples. When I first came to Singapore, I went out into a farm and I saw this tree, and this tree had pink plastic bags on it, and I thought to myself, wow, a plastic bag tree. I never knew that plastic bags grew on trees. You're smiling, or at least you're laughing, because you have the domain knowledge that plastic bags do not grow on trees. They're oil-based or petroleum product-based. But supposing I didn't have that knowledge, I might write a research grant to improve the yield of plastic bags on trees, or to change the color. And that's basic science. We don't know something, we need to find out and do the domain knowledge. So whenever you're making an inference or making a design, you need to understand that the conclusions you make, the decisions and inferences you make, are only as good as your domain knowledge. You need to know at times what you don't know, so you can get help from the people who do. One of the other tools I came up with back in 2000 was I was looking to develop my course in systems engineering. And so I asked around, what are the requirements for a course in systems engineering? And nobody had any. I thought that was strange, because we're systems engineers, we deal with requirements, but in education there are no requirements for what we teach. So I said, okay, let's work it out on what systems engineers do. We could take Jerry Kitchen's 5 layers, we could take the phase or the state in the life cycle, we could look at what they actually did. So we noticed that systems engineers, for example, who are eliciting and elucidating requirements, are working in area 2B. Systems engineering who are testing and integrating systems are working in 2F. And so they will have a different view of what systems engineering is based on what they do. And so those working in 2B will have a different view of those in not 2B. So what is systems engineering? To be or not to be? That is the question. Sorry about that, I couldn't resist. When you think the way I do, you see connections that other people don't. So systems engineering, as practiced and taught, is mostly in layer 2. And operations research, or system of systems, is up in layer 3. The systems thinking people are up in layer 3. They are using systems grouped together to achieve something, so no wonder they say you don't need to understand. But the traditional requirements to integration and testing version of the systems engineering process, or the system development process, is a white box view of systems engineering, where the operations people or the systems thinking people are using it as a black box. This sort of allows me to come back to what I was talking about earlier about the elephant. If you take a look at the different publications and perceptions of systems engineering, you can map them into something like this, where you put in the type of systems engineering. I didn't talk about CAMP because of less time. Pure applied and life cycle all are part. You can take the different publications and you can see what's in them. And you can see they're all different, because they're all discussing a part of the elephant, except number 9, which covers everything. So what can you do with this understanding? You can define the information you want by positioning your area of activity in the HKM framework. You can identify the camp or perspective that you need to view it from. You can define the mixture of pure applied and domain systems engineering, and then find the book or course that will provide the information. You can ask somebody in an Incose working group or cafe or fellow student, get a coach or a mentor, and so on, who's faced the type of problem before. For example, you want to get a master's degree or take a course on systems engineering. Eileen Arnold and I took a look at what was being taught in master's degrees back in 2013 based on what their websites said they were teaching. I'm not going to go into the numbers here. If you're really interested, you can read the publication. But what I want you to see are the gaps. You can see that there are gaps in Hitchens' layer and the state of the life cycle. So all courses are not equal. And in fact, in 2 degrees, you could get a degree in systems engineering without taking a single required course in a systems engineering topic. I actually found some requirements. The 5 top aspects of the engineering design process that best equip secondary students to understand, manage, and solve technological problems, multiple solutions to a problem or requirement, oral communications, ability to handle open-ended, ill-defined problems, and systems thinking. Well, when I took a look at what the website said those degrees taught, only one had a slight amount of systems thinking. Number 11 was my degree, and of course it covered these things because I had the focus on systems thinking and beyond in there. So at the end of that presentation, I put up this slide. Academia is not teaching the right things in systems engineering courses, and I put in a couple of references. And then I said, who wants to join a new Incose working group to address these issues? Incose's response to the presentation came in an email from Cecilia Haskins. I was banned from presenting at the IS for the following 2 years. No further comment. Let's talk about complexity. There's a dichotomy in complexity. There's a need to develop new tools and techniques to solve these problems, and the complex problems are being remedied successfully. So we take a look. There was a doctoral dissertation that said the problems posed by complexity seem to be unmanageable. Or Batyam quoted the chaos study. Actually, I think he misread it because in the chaos study the cause was not complex. It was poor management. And the Incose version as of 2013. All these people here need to get out of their box and look around because all these systems are handling complexity without even thinking about it. Let's have a little lighthearted break. I'll ask you the question, why do men say ladies first? And the answer is risk management. So what's the difference between system engineer, a good systems engineer, and an outstanding systems engineer? A systems engineer creates the system the customer asks for. A good systems engineer creates the system the customer wants. And an outstanding systems engineer creates the system the customer needs. Never seen this in a book, have you? Let's think about it. Let me tell you about George. George is a systems engineer. He consciously reads every one of the hundreds of requirements provided by the customer. He's got great difficulty understanding what the customer really wants. He even tries to relate the requirements in a hierarchical structure. It doesn't help much. He tries modeling the requirements using an MBSE tool. He still can't get a complete set of requirements from the customer, and the customer changes the requirements every time George talks with him. Does this sound familiar? George is a good systems engineer. He's following the systems engineering process based on the standards. The customer is unhappy. The project is going nowhere. George cares, but he's got no idea what to do about the situation. He's stressed out. His family life is suffering. He's losing his friends. He doesn't have any time to relax or anything because he's trying to be a good systems engineer and understand what the customer wants. And even if he can understand what the customer wants, he may not have defined the system the customer needs, which is one reason the customer keeps changing the requirements. George is working in the B paradigm, but he needs to use the stress-free approach used by outstanding systems engineers. Let me show you the difference. A systems engineer talks to the stakeholders and the customer, who is also the stakeholder, and from that generates the requirements and gives the customer the system that is asked for. The good systems engineer, on the other hand, puts in some feedback, might build a model, and as the system engineer understands more about what the customer is asking for, will go back and explain some of the ramifications and the ideas, and the customer and the stakeholder will say, hey, that's a great idea, let's add to it. And so the requirements keep changing on them. Everybody's unhappy about it. The outstanding systems engineer works differently. See that generic system requirements block in the middle, not taught in the textbooks? The outstanding systems engineer understands the problem and then looks at what's happened before and builds a model which includes not only the requirements the customer is asking for, but also what I call system generic requirements. These come from laws and regulations that affect the system. They might be environmental, they might be legal, whatever. They also come from the generic requirements that are inherited from similar systems, that similar systems need to meet these requirements. The outstanding systems engineer builds this holistic model that is complete, or much more complete than the one that the good systems engineer does. So as a result, when that model is turned into requirements, it is pretty much good. And I think this is one of the goals of model-based systems engineering. But what this really is, it's back in the A paradigm. We didn't have the tools that they have today to build models, but we could use PowerPoint, we could use drawings, we could even do a little simulation depending on the system. The outstanding systems engineer is nothing new. Well, what can you do with this understanding? You can follow George's footsteps. You can become an outstanding systems engineer. You can learn how to apply systems thinking and beyond to problems. You can learn how other outstanding systems engineers tackled the type of problem you're facing, network with others pursuing the same goal. Join my Facebook group on tackling complex problems. I'm just starting it. You get some benefits and the drawback. When you really use systems thinking and beyond, you see things differently to other people. You make poor jokes, and you've suffered through a couple of them today. You ask uncomfortable questions. You challenge assumptions. You're also comfortable with knowing that in some instances you don't know. You see solutions where other people see problems. Nobody realizes the achievement you made because there weren't any problems. The squeaky wheel gets the attention. Your project didn't have any problems, obviously. You also see what could have been, so you're dissatisfied with your outcome when everyone else is raving about how good it is, and you're in a different paradigm. So the lessons I've learned, you can't really solve a problem unless you understand the three domains. You need to view a problematic situation from a number of perspectives in a system and systematic manner. You definitely need systems thinking and beyond to create innovative solutions. Communications is the key to success, and it's also the key to achieving recognition, because you need to show people that you have identified problems and you're mitigating them. And we call that risk management, and that's not only on the system, but it's also on your career. And I've developed two tools that can help do that. CRIP charts, categories requirement in process, and enhanced traffic light charts, and there are YouTube videos on both of them. So you want to be an outstanding systems engineer? Join my Facebook group, read my published papers, download them from Incose or my website. And I've actually taken most of my papers up till about 2015 and published them as an anthology in a framework for understanding systems engineering. I've taken the perceptions that I've talked about today and a lot more, extracted them from the paper and published them in Perceptions of Systems Engineering. And holistic thinking goes into a lot more detail on systems thinking and beyond. And if you like those books for free, send me an email and I will send you PDF versions and talk to me about your problem. My new career is a coach or a mentor. I've been a successful systems engineer and I've got the papers and plaques to prove it. I've been an academic and I've been recognized in my field. Now I'm a coach and a mentor. This is a situation awareness state diagram, which I invented, at least as far as I know. There are 6 states, but you may not progress through them in linear format. The basic state is you don't realize that something needs to be changed, either because it's wrong or because it could be improved. And I hope that I have taken you from state 1 to state 2 today, and now it's up to you. Are you going to go into state 3, 4, 5, 6, and hopefully 6B? Thank you for listening. If you have any questions or comments, I'm perfectly happy to answer them, and I will provide free PDF versions of the books, as I said before. Unfortunately, I cannot give you free books. I cannot give you free copies of the books published by CRC Press, but I can give you a discount code. Thank you very much. I'm done.
Thank you, Joe. I don't think I've laughed at systems engineering presentation as much as I did with this one, with the jokes and stuff. So now I'm going to open the floor up to questions. If you have questions, feel free to submit them. There's one from Steve Sutton there, Joe. Do you see that in the chat?
Steve, I haven't looked at the graduate curriculum for at least 4 years. So if it's changed since then, the answer is I don't know. If it hasn't changed since then, I focus on the pure systems engineering topics, which I never saw in the graduate curriculum.
Okay, any other questions?
Yeah, Bob Berkovitz.
Yeah.
I have a question. Well, a comment, excellent numbering of slides, so we could question the one, point out to the ones we have questions. Right at the beginning, looking at the camera and the whole lighting environment was an issue. That's, the environment is part of the problem. And the linkage between hierarchies is very important. And I knew that, the operations people on the aircraft carriers, when they're going to upgrade the whole radar system, don't radiate in an unsafe direction. And it took NavAir a couple of years to figure it out, but they never, the beginning in 03 and 04, talked to the carrier operations people. Eventually they solved it and got a huge contract for 72 upgrades on aircraft.
Okay. As a comment, Bob?
Yeah, it's more of a comment looking at the interactions, the linkages between the hierarchies. You mentioned some of that, I guess, and also in the process from mission to ConOps, all the way out to the right side of the V, where you have operation, maintenance, logistics, and upgrades, where you could eventually have a problem if you don't address the disciplines like supportability disciplines, EMC, and so on.
Well, I can get into that in several ways. One of the things I teach, or I'm not sure I teach it actually, but what we used to do at the beginning of a program was go out and take a look at the site. If we're going to install a radar system on a camera, on a carrier or whatever, go out and take a look. Go see where it's going to be, look around you at the adjacent systems and see if there's going to be any problem, because it's going to have to shoot through the conning tower or whatever you have on a carrier. I'm not sure what the terminology is. Or even if it's even as simple as if you're going to install a system in a building, make sure it can be taken in through the gate, through the door. I have a wonderful picture that I took at the at the National University of Singapore of people with a great big crate on a crane because they couldn't fit the system in through the door. They had to bring it in a different way. And they didn't realize that until they actually got there. And so those points are important. And then when you talk about the issue of sustainability and so on that need to be considered early, we had a discussion on that in the Fig Cafe yesterday. I do that at requirements time. I add attributes to requirements using the object-oriented principle that says, if I have a requirement, what's the risk involved in the requirement? What's the priority and so other ones, and you start discussing and examining that before you actually accept the requirement, you understand the full impact of the requirement. It's like doing a feasibility study on each requirement.
Yes, Dr. Kasser, I've got a question for you. I really enjoyed that. That was a really fresh look at how we teach system engineering and how we do system engineering. My question is, in the Incose handbook, I think at the beginning, Incose does a rather, in the handbook, they do a rather good, decent job of explaining that there are different system engineering processes out there. And while some of the steps are different in the processes, they all kind of hit at the same idea to get to an end goal of engineering a system. And I just wondered if you had, like, for instance, NASA, DOD, CIA has a different process, DOD has a process, Incose has a process, NASA has a process, but all of those four that are compared in the Incose handbook all can be credited with having run their process successfully for many, many systems. And I just wondered if you ever matched a particular process up to the successfulness of the engineering that it was able to be used to produce, particularly like for NASA. NASA's process is highly respected, and they do have a lot of achievement using that process. So it's kind of hard to say it's not working.
Well, I learned my systems engineering in NASA in 1970 or so. But if you look at all those, if you take all those different processes and you break them out into the lowest common element, the lowest element, and you put them into an n-squared chart or design structured matrix, depending on what you use, you can see that each of the processes are different groupings of those small elements. They group them differently. You can also see that in some of the processes, there are items that are missing, that are not in the other processes. Like I pointed out in the systems engineering processes, that the front end was missing. But what they really are, and it's alluded to in 1220, is they are versions of the problem-solving process.
Oh, okay.
And that's what I showed. So what I was trying to say with the egg diagram was, don't teach the egg diagram, teach the problem-solving process, because the egg diagram is sort of the problem-solving process, but it's using, it's not using abstract language, it's using physical language. It's saying we do requirements, we do analysis, we do this and the other. Whereas the functional language is understand the situation, conceive solution options. And then you can say, if you teach it as a problem-solving process, you can say, in the requirement state, the problem is that we have to write the requirements. So we first have to understand the requirements, and the solution will be a matched set of specifications. There are different ways of writing requirements. We can share, for example, we can say the system shall be more than, not less than, or whatever, and then we can choose the wording for the best clarity. When we go into the design state, again, it's the problem-solving process, but in terms of pure systems engineering, but the activities that we're doing, that's the applied systems engineering, are different because we are working with designs, whereas in the previous state, we were working with requirements, but it's still problem solving. And so the pure systems engineering remains the same wherever you are in the waterfall, or I call it I consider the V diagram as being the waterfall with the last states turned up. And I went back and looked at the origin of the V diagram, and it wasn't developed as a model at all. It was somebody showing It was a customer showing it was a contractor showing a customer the effect of making changes.
Okay, so, well, if you had to apply that like to the, NASA recently had a huge success in achieving a first flight on a different planet. So if you look at that domain knowledge that they had, the gravity, the air pressure, the, not air pressure, but the, let's say the gas pressure, I guess it's air on Mars, but the density, all those types of things, were they able to make measurements with prior visits to Mars, or did they just have to make guesses for the domain engineering?
I have no idea, but they had measurements of the atmospheric pressures and conditions. They've got these large thermal vacuum chambers. I don't see why they wouldn't have flown that thing in a chamber with their best knowledge simulation of Mars.
So from your three domains, then, what were they in all three of them in order to achieve that success?
Yes.
Okay.
I mean, I can tell the story of a failure that they probably learned from when they flew the instruments to the moon on the Apollo program. One of the instruments was to measure gravity waves, and it had a pendulum, and the pendulum had weights on the end. And the story goes that they forgot to change the weights. So they tested it on Earth with one set of weights for the terrestrial gravity, and they forgot to change the weights for the lunar gravity. So it was just out of the range and the instrument didn't work. That's the story. So if they have the history there and they remembered it over the last 50 years, 40 years, 40, 50 years, wow. Then they would have learned that lesson.
Thank you. Great answer. Thank you.
And remember what I said about the excellence is on the people. If you have, as Bruce Lerner pointed out in the chat group, if you have a terrible process, but you've got good people, it will work. You can have a really good process and not very good people, and there will be problems.
Thank you.
I think John Clark put something in the chat window. John, do you want to unmute, maybe ask your question?
Right. Thank you, Clinton. Well, in the chat, let me read the question. There are actually several questions that are related in this one question. Why do Incose and the US DoD require that the constituent systems in a system of systems be operationally and managerially independent? Why do they exclude dependent systems? Are there really any 100% operationally and managerially independent systems? Aren't all systems dependent on some other systems? Can you name any 100% independent system?
First question, you're asking the wrong person. Asking COSI and the DoD, don't ask me. I can hypothesize that there might be a legal requirement because in the US they separate contracts. Somebody who develops something is not allowed to bid on it later, from what I remember from my time in the US all those years ago. As far as operationally and managerially independent, I don't think there are.
I agree with you. There are none, in my opinion. I don't know why Incose and the DoD insists on this.
I'm trying to do a sensitivity analysis on the words that you're using. If you're using operationally as the organization that runs the system, and managerially as the organization that owns the system, they still are not independent.
Correct. I agree. And that's the way I'm using them.
So I will answer your question as because they don't realize that their version of systems engineering doesn't work.
Correct.
And once they realize that, they may change.
Hey, Dr. Kasser, it's Dave Fadley. I agree with your general principle here of trying to understand a problem and define the problem and start with that, and something I've been doing for a number of years as well. What I found, I want to see what your input would be. I found that although the customers or the person who is sponsoring that particular thing, we're all under time pressure, and usually they don't want to take the time, and they usually want to get the first something they think is the problem and to solve. Maybe it's just a symptom of a problem and drive it down there. And so it's a lot of influencing has to go on up front. And sometimes that works, sometimes that does. I want to see through your experience in consulting, what tools and techniques tend to work in a really, these time crunch, very impatient world that we live in.
Yeah, unfortunately, people screw up, or customers put the seeds of doom into projects before the projects really started. And I got taken off a project in NASA because I asked the customer a question. We were sitting around right before some work was done. The customer wanted a fiber optical ring architecture because there was a lot of data coming in and there was a lot of data going out. The customer read an article in the journal that says FDI fiber is the way to go. And he said, we're going to use that. So very politely, I said, shouldn't we do an analysis first? The customer said, no, we're going to use a ring. And 2 weeks later, I was taken off the project for being arrogant. There's a real world out there. And in academia, we teach the ideal world, but we also have to teach that there are two axes in a project. There's the planning axis and there's the doing axis. And you can spend all your time planning and not have any resources left for doing, or you can do no planning and spend an awful lot of time doing. Or you come up with the optimum for that particular project in that particular situation. That's why we do feasibility studies. And if the customer doesn't want a feasibility study done, okay, then tell the customer they'll have to double everything, period. If they still want to do it, then you have to make a decision. Are you going to go along with that doomed project and waste the customer's money, or are you going to say no? I've also said no on several occasions. My contract at the National University of Singapore was not renewed because I refused to teach a 10-year-old course in systems engineering.
Okay, do we have any other questions? We'll have some time after, if anybody wants to stick around and chat. But if there's no other questions, I want to first thank Dr. Kasser virtually here. So I'm just going to share our certificate of appreciation, and I'll send you a PDF version of this. But I want to thank you for giving us this talk, very informative and even humorous at times. Found it very, very enlightening. So I want to thank you for that. And now we'll have Dave Aldridge auction off your book on holistic thinking. Dave, you ready with the big wheel of Incose fortune?
Yes, I am.
Okay, go ahead and present that.
Can everybody see that now?
Yep.
Okay.
And yep, go ahead and spin
We
it.
have 51 people eligible tonight. I think that may be a record. At least that's the most I can remember for a long time. And the winner is Jeff Baldwin.
Congratulations, Jeff. I will use your registration email to contact you to get your mailing information, and you will receive that in the mail. So that's the end of tonight's presentation, and feel free to hang around if you want to chat to some old friends or not. Otherwise,
I have a question for you.
me.
Which parts of the presentation did you laugh at? I just want to be sure you were laughing where you're supposed to.
I'm pretty sure it was all the ones that you meant to be humorous. I mean, the Dilbert comic, certainly. Some of the metaphors you were using there, some of the, so yeah. No, I can't go slide by slide, but I just know that mostly I'm pretty, humdrum through these, and this one I'd say maybe like three or four times I put out a chuckle.
It looks like we do have a chat question from Ricardo Rodriguez.
Oh, Phil, where's that? I don't.
You see it in the chat?
Oh, feel free to
I don't know. I guess if he's
unmute
online,
Ricardo.
let's let him ask the question, unless he can't.
I can read it here. It
Oh,
says,
no, it looks like he's unmuting. There we go.
Hey, hello.
Hello.
Well, I was just asking that for someone that is just trying to apply system engineering and selling it to an organization, where should somebody start to look into besides of the Incose body of knowledge? Because what I see is main focus in Incose is about processes, but yeah, there's always this emphasis on process is not the focus, but delivering a system. So yeah, I'm wondering where should I look for more information or something that could help me that is not in Incose's website.
I would not look in Incose. I don't know what your problem is. If you want to tell an organization that, hey guys, we need to be doing systems engineering, you're not going to achieve it, because you're now getting into the problem of organization change. So if you want to do that, go look in the literature on business process reengineering, organization dynamics, total quality management. That's the domain that you're working in. If you're on a project and you've got a specific problem that you need to solve, then you do it in the systems engineering way, but you don't tell them you're doing systems engineering until the project is over, and then you say it worked because we did systems engineering. I mean, this happened to me. Back in the 1980s, I was a subcontractor working for L'Oreal, which is now Lockheed Martin, who was working for CSC, computers, whatever they were, I forgot. And my customer had been to a course, and he'd gone to a course on joint applications development, JAD. And so every time we had a meeting, he wanted to run a JAD session, until they got to the point where when they saw him coming, they said, no JAD, go away, even before he opened his mouth. But what JAD really was, if you think about it generically, It was brainstorming in a certain way. So when I ran a meeting, I was using exactly the same techniques, well, twisted slightly, that he wanted to do in JAD, and I never told them what I was doing. I was just using active brainstorming and those perceptions. I realized later what I'd been doing because I was doing a lot of this without thinking. And people, I used to come out of the meetings and people used to tell me, how do you know so much about our domain? And I just smiled because I didn't know too much about their domain, but I knew the questions to ask and I could give them back their own words and build on the questions, like using the 5 whys. I would just give them back their own words with an occasional what and how and are you sure? And they would talk themselves through their own problems. And so don't mention systems engineering, just use it.
Thank you.
Dr. Kasser, Bob Berkovitz, I wanted to find out your contacts so we can get those PDFs. You said you had 3 of them. And the other thing I really liked when you talking about getting something inside the doorway of a building. Well, in the E2C, when they had a preamp and amp cabinet on the upgrade, they didn't take a cardboard model to see if they could fit into the door on the E2. So they had to break the preamp and the amp up. And it delayed them a few months. You know, mechanical engineering and EMI and E cubed and electrical, you know, because you had to connect the preamp to the amp cabinet. So that was an oversight in the big picture. That was about, 03, 04.
Yep. I mean, that's why you do a site survey.
Exactly.
And unfortunately, it's something you learn from experience once, and then you remember it the rest of your career, but you've got to remember to tell other people about it.
Well, lessons learned, say on the example in A10, it doesn't carry on when you have a lot of different contractors doing maintenance and upgrades and not looking at the, some of the environmental requirements and previous test data, and they ignore certain things and you have problems coming up. It's happened a couple of times when they changed contractors for the maintenance and upgrades.
Yep.
Thank you.
We generally have a requirement at the end of a project to document the lessons learned, but there is no requirement to actually read it before you start a new project.
Or carrying on into the future, lessons learned and forgotten because you have different personnel and maybe different contractors.
Well, you see, now you're in one of the gaps that I mentioned in my talk. In the problem-solving process, you understand the situation and you've got a pretty good idea what you think the problem is. What's the first thing you do?
Well, I try to see what had been done before. That's usually one of the things. And again, that's lessons learned, I guess.
Yep. The first thing you do, and not too many people answer this correctly, is look around and copycat. What has somebody else who's faced the same problem in the past, what did they do? And how does that relate to to my situation? And TRIZ, T-R-I-Z, uses that principle. And in TRIZ, they say, if you can arrange your problem into one of, I think, 40 something patterns, you can then look and see how people who've had the same pattern or what they did about it in their situations. And that gives you a starting point. So this step, this additional step in the process that's not generally taught helps you create your own innovative mistakes and not make the ones that other people, the boring old mistakes that other people made in the past.
That is a way maybe you can design a problem or requirements for using artificial intelligence when you're doing a similar system and upgrades to look at what happened in the past and learn from that. It can be pretty complex because you have all aspects from the development design into logistics and maintenance upgrades.
Now, you're now addressing something that I've been harping on for 20 years. Why can't we have a requirements tool tell us whether it's a good or a bad requirement? I developed a teaching tool that will do that based on a list of poor words in exactly the same way as a spelling checker picks out poor words in a document. So you can put a spelling checker into your requirements tool that looks at words like easy, maximize, and or, which may mean you've got more than one requirement, which makes it difficult to separate it out for testing. And I've had that for 20 years.
Well, I have a question there. You have to look at the differences if it's a similar system or the same application with upgrades. Then you're going to have to do a comparison. And, you know, a lot of people don't do that, particularly if you have a different contractor on the upgraded or a modified system.
Yep.
Okay.
And you've got to understand like software incompatibilities, where a program, even on a Windows platform, programs that run on one version of Windows will no longer run when Windows gets updated. And in hardware, you've got the problem of spares when systems get upgraded or not, as the case may be. That was DMSMS.
Oh, you're talking about interface control also, which was, had some pretty good people at Hanscom in the late 70s working that on projects. That's one of the requirements. And a group addresses that.
Yep.
Yeah, thank you.
Okay, there was one other thing. Did we get our picture?
Not really. I don't know. So yeah, if a bunch of folks want to turn their videos on, we can take sort of a broad snapshot of. I think we can only capture like probably
Well,
like.
you can always go to the second page, but I don't know how to do that. But I guess Jim DeCamp is a way of doing that. Jim, you still online there?
I can take a snapshot, or yeah. All right. So I got one. Maybe save that. Okay.
Oh, what happened? I was supposed to put my Tom Selleck look on tonight. Oh, well, something's wrong.
All right. Well, yeah, like I had mentioned, we're gonna make the slides and the recording of tonight's lecture all available as an actual after report on our website, Chesapeake chapter website. It might take a week or so to get up, but it'll eventually get there.
Oh, it looks like John Clark may have still had another message, but I think Dr. Kasser did answer it in the presentation.
John asked me, why did Incose prohibit you from presenting an IS for 2 years? During the I made that presentation where I showed that we weren't teaching the right things in academia. There was a member of the audience from Stevens who started complaining that what I was saying was not representative of his institution, because that was one of the institutions, and I didn't. It's in the so. The data from, he kept saying that the data from his institution was not correct. And I kept very politely saying I was using the information that was on his institution's website. And if it wasn't correct, then the website needs to be changed. Well, he complained to David Long, and a group of Incose people got together and decided to ban me for being too confrontational. Even though other people in the who were in the academic panel at the time said I wasn't. I got the ban rescinded because as an academic, when you're banned for publishing, that is a really serious thing. And it also deprived the Incose Singapore chapter of the chapter award points.
And what
And
year
so
was that, Joe?
It was 214.
Okay.
So the ban was from 214 to 216, but it was lifted. But I went to one symposium in 215 to talk to the relevant people about it, but nobody wanted to talk about it. And I have not been to a symposium since, because I'm still under notice that if I get if somebody complains about me at a symposium, I can be ejected. And so I'm not going to the expense of going to a symposium if somebody can kick me out because they don't like me. I think my comments about Incose not doing the right thing and trying to change Incose over the last 20 years has upset too many people. But you know something? I don't care anymore. And this was being recorded. Okay.
Dr. Kasser, thank you very much, Bob Berkovitz. I enjoyed the whole set of slides and your comments.
Okay. Somebody made a comment that they wanted to know my email.
Yes,
so they can,
thank you.
They can get the books. That was my test to see how serious you were. If you really wanted the books, you would take the time to Google and look it up.
Oh,
If you had just taken advantage of a free offer and the books would sit on your hard drive and never be looked at, should I waste my time sending them to you?
It's academic for me. I bought all three, so.
just the titles so we can look them up, or just look it under your name.
You send an email that says, send me the books you offered.
Oh.
That's the easy way of dealing with it.
Good, thanks.
Okay, well, thank you all for coming and paying attention and staying till the end. You can reach me on the Facebook group.
All right, I'm going to close up the meeting room and hope to see you all at the next event.